Welcome back to Calculus 1. This is our third part of our lecture on the derivatives of polynomials and exponential functions, where we will get to the fourth and final part laid out from lecture 1. Recall we were splitting this topic into 4 parts: derivative of constants, derivatives of powers, derivatives of polynomials, and finally now, derivatives of exponentials. So let's get to our fourth and final part with derivative of exponential functions. Now, this was a topic that was introduced probably thoroughly in your pre-calculus course. You first probably had it introduced as the form f of x equals a to the x, where a, what we call the base, is positive and then not equal to 1. And that's just for making sure this is defined. That way we don't end up with any square roots of negatives, any stuff like that happening. Now for calculus, we're going to focus primarily on one important base number. It's why this was hopefully hammered in your pre-calculus course. Hopefully you saw lots of exponential functions with base e, where e is what we in mathematics call Euler's number, which is approximately 2.72. Realize, like pi, it has an infinite non-repeating decimal representation. Okay, so we're going to see that this exponential function, the base e version, e to the x, has some rather remarkable properties from the perspective of calculus. Now, you don't have any reason to expect that yet, but we'll start to see that very quickly. This is a very important function, not only for mathematics, but for most of the sciences, as well as engineering. Okay, so here is our kind of starting place. We have a function. And at this point in a Calculus 1 course, we just are interested in what is the derivative for different functions. So if f of x is e to the x, what is f prime of x? What is the derivative of e to the x? Now, I could just tell you, but you're not here for that. You want to learn, like you want to know at a fundamental level why all these mathematical facts are true. Now, we're going to take a look at one final application of our limit definition because there's kind of some problems with some previous rules. So let's kind of approach this. It seems to be simple. E to the x is a simple looking function. What is its derivative? I'm going to argue it's not as simple as it may seem. All right, so let me intentionally try to fool you, lead you into a trap, derail you. Let's start by talking about the power rule. Well, we have, exponents here, powers, e to the x, right? There's powers. Well, let's think very carefully about what the power rule applies to. A power of x, x to the n. Now we have the power rule stated here, the derivative of x to the n. This rule is valid when n is any real number. It doesn't have to be a positive integer exponent. And you bring the exponent n down and then subtract 1 from the power. All right, seems simple, right? Keep in mind, I am intentionally trying to mislead you. I'm trying to lead you into a trap. I want to make sure you see and understand the common mistake I find this point in part of Calculus 1. All right, so let's start with an example to, get you thinking. Again, I'm trying to lead you into a trap. Seems simple, right? The derivative of x to the 9th. That is a power of x, x raised to a number. So we apply the power rule, 9 times x to the 8th. That's the derivative of x to the 9th. Now that is mathematically correct. There is nothing wrong with that. But now that I have you thinking about the power rule, see what you can maybe determine for the derivative of e to the x. There's a common incorrect answer I get, and I hope that right now you make the common error that I find. We'll check in a few seconds. Okay, now what is the problem here? The power rule for differentiating x to the n only applies to a power function, x raised to a number. E to the x is not a power function. So we can't apply the power rule because e to the x is not a power of x. It's flipped. It's a number raised to the x power. Now, again, just to pause so you really get this, that answer there, x times e to the x minus 1, it's the kind of reasonable answer you might get by trying to mistakenly apply the power rule. You bring the exponent down and then subtract 1. That only applies for powers of x, x raised to a number. E to the x is an exponential function. Powers are where the base is a variable, the exponent is a number. An exponential function, that's flipped. Now it's the base that is a number, the base is e, and it's the exponent that's a variable. So for that reason, we cannot apply the power rule to differentiate e to the x, because e to the x is not a power function or a power of x. So the power rule does not apply. Realize that answer there, x times e to the x minus 1, is the most common incorrect answer I get. I understand why a student would make that error. It looks like the power rule applies, but it does not. So we can't apply the power rule, reaching that answer. Now that just brings us back to where we started. While the power rule is valid for differentiating x to the n, the power rule is not valid for differentiating e to the x. So we are yet again stuck. We have a function here that none of our current differentiation rules are applicable to. So what can we resort to? Well, we can always resort to our lovely limit definition. Yes, we're going to apply it one last time here. We've been hammering this in so that way we're not stating mathematical results out of nowhere. I refuse to do that. I like to make sure each idea leads into the next in a very logical fashion. Now, if you are not interested where this formula comes from, you can just click the few slides and the answer is e to the x. But some of you might be interested to see how all this fits together. So let's apply our foundational idea, the limit definition of the derivative, one last time. This is probably the last time that we'll work it out in detail from here on out in the course. All right, now we're going to apply the limit definition here to the function f of x equals e to the x. Okay, so we plug in x plus h and get this term e raised to the x plus h. And then we subtract f of x, subtract e to the x. Now we're going to simplify this in some non-obvious ways. Again, you have to be very comfortable and kind of very fluent in algebra to be comfortable with this. We're going to rewrite e to the x plus h. We're going to rewrite that as e to the x times e to the h. Believe it or not, this is a very important trick throughout the calculus sequence. I don't hear it often described as being incredibly useful, but we are reversing that basic exponent rule there. A to the m times a to the n. Recall when you multiply bases, you can add their exponents. We're going backwards. We have addition in the exponent, which means we can rewrite that going from the right side to the left as a product of basically what we're adding in the exponent. So e to the x plus h, we can break that apart as e to the x times e to the h. Make sure you see that. Pause if needed. Work that out in algebra, going from the left side to the right and vice versa. All right, so we'll use that result there. All right, what we're going to notice now is we can simplify this. Notice within the numerator, each term contains a factor of e to the x. So we can factor that out. We can factor out e to the x within the numerator. We're then left with, in parentheses, e to the h minus 1. If you're not certain of that, distribute the e to the x back in, and you should get the numerator in the line above. All right, what can we do from here? Still, it just looks like we're left with a complicated fraction. I assure you we're going somewhere. Let's think closely here. we have two variables, I'll say, or things that look like variables, x and h. One of them really is a variable. One of them, we're not interpreting it as a variable right now. Now, the key is to realize what's going on with a limit. Notice here, this is a limit as what approaches 0. What is approaching 0? H. So that means h is changing, getting gradually closer to 0. That means h right now is interpreted as a variable. X then, or e to the x, is not interpreted as a variable. If something's not a variable, it's pretty much just a constant. So we're going to think here of h, or anything with an h in it, as being a function or variable. Anything involving x is viewed as a constant. And that's because this is a limit as h changes, gradually getting closer to 0. Now we're going to use some properties of limits. That goes back a while. It goes back to our lecture on the limit laws. We have a constant, e to the x, which we can pull out in front of the limit. This is kind of our stopping point, unless we want to get into some highly technical mathematical arguments, which I do not in a Calculus 1 course. This is where we're going to leave it. Now, we have encountered the limit here of that expression as h goes to 0, but we did so very early on with one of our first examples using the numerical approach. And the only difference is, earlier we used x as the variable. We did see numerically, very early on within our first lecture, the limit of a function, that the limit as x approaches 0 of e to the x minus 1 divided by x, that equals 1. Go back and review that. Our first real lecture, the limit of a function, it was example 1. We did it with the numerical approach to at least verify that. Okay, so we just use that here. The only difference is now h is the variable. So that limit approaches 1. And then our answer here is e to the x times 1, which is just e to the x. Now, think for a second, what was the function we started with? E to the x. What does the limit definition give for f prime of x here? E to the x. And this is a very important but peculiar result. E to the x is a function which is its own derivative. And I kind of get excited about that. It's kind of interesting mathematically, and it leads to a whole lot of kind of interesting results within science and engineering. Some of the reason for how the universe looks as it does, for how, I'll say, atoms and molecules behave. This is thinking from quantum mechanics and physics. Some of those rules or laws of physics are because e to the x is a function that is its own derivative. That's well beyond the scope of our course, but some of you might be working eventually to get to that. So it all starts here. All right, now let's just summarize what we just worked through here. We found that the derivative of e to the x is e to the x. If we differentiate e to the x, we get the same function, e to the x. That's not made up. Notice from what's on the screen here, that logically follows from applying our limit definition. Nothing in mathematics is made up. It's all built upon a solid foundation, which I'm trying my best to make sure you kind of see. Some of you don't care about that, which is fine. Some of you going the full distance all the way through Calc 27 might be interested in that foundation. All right, now this result is so important, we're again going to put 2 boxes around it since it's so important. So let's kind of go ahead and summarize before we get to kind of some examples. All right, so this is, again, a very important result for the derivative of the exponential function. Usually in calculus, we refer to e to the x as the exponential function, since e to the x base e is mathematically the only exponential function of importance, I'll say. We're gonna see later and hold off on exponential functions of other bases. Okay, so this is a really simple result. E to the x, it's a function, which is its own derivative. And again, there's some, I'll say, laws of physics that kind of are a consequence of that fact. But you have to get into the highly technical physics courses, quantum mechanics and stuff like that. Okay, now to prime you for the next example, example 3, which was one of my favorite examples to give in my calculus courses. It's a really simple example requiring no elaborate or lengthy calculations. But example 3 does test your conceptual understanding of everything so far. So let me prime you for example 3. You want to keep in mind that the derivative of a constant is 0. The derivative of a power is this power rule. You bring the power down and then subtract 1 from the exponent. And then this new, I guess we'll call it exponential rule, although there's really not an official name for it other than the derivative of the exponential function. The derivative of e to the x is e to the x. Now you definitely would want to pause and at the very least have these in front of you before we turn it over to example 3. So pause, copy these into your notes if needed. And when you're ready, we'll jump to one of my personal favorite examples to give in my calculus courses. All right, are you ready? Are you excited for it? Again, it's one of my personal favorites. Let's get to it. Example 3, simple question, find the derivative of this peculiar function, y equals e to the x plus x to the e plus e to the pi. I'd like you to pause and really think about this. I'll give you some hints in a little bit. So pause and give yourself an attempt. And then in a little bit, when you go to unpause, there'll be a hint on the screen. So pause, really think about this. We'll check in a little bit. All right, you ready? Again, one of my personal all-time favorites to give in any of my calculus courses. Now, why is that? This question is very deceptive. I'm trying to fool you. I'm trying to lead you into a trap. Reference there. Okay, what type of function is each term? Now, so far, I primed you. I got you thinking. Try to identify some of these terms as being constant functions or constants, power functions, or exponential functions. Now with that hint, maybe make a second attempt, pause again, and see if you can reattempt this. Okay, was that enough of a hint? Well, let's start with our function. Again, this requires no lengthy or elaborate calculations. Those examples are coming up within a lecture or two once we get access to the product and quotient rules. But we are not there yet. This problem is more a conceptual problem, just making sure you understand what each term in this function represents. Okay, e to the x is an exponential function. X to the e is a power function, a variable raised to a number. And even though we're writing it with exponent notation, e to the pi, that is a constant or number. Now, I have no idea what e to the pi is, but e is a number, pi is a number, and I at least know that a number raised to a number is a number. So e to the pi is a constant. It's just a number. Now, with that in mind, it should be very easy to differentiate this term by term. We apply the exponential rule to differentiate e to the x. We apply the power rule to differentiate x to the e. And we apply the constant rule, not the constant multiple rule, the constant rule to differentiate e to the pi. And the calculations, provided you understand why we're applying each, are rather simple. That's why I like this example. It really kind of tests how well you understand what everything is at the level of formal mathematical notation. It makes all the difference here for this example. So if you calculate your three derivatives, provided you understand those three differentiation rules for the derivative of a constant, the derivative of a power, and then the derivative of an exponential, we should get to here. And again, notice very minimal work, but it's definitely more conceptually challenging. All right, now before you advance to example 4, make sure you thoroughly understand example 3 here. When you're ready, we'll get to our final example for this part. This is part 3. And then our final example also for this lecture. Again, this lecture was very dense. It's important. So we split this into 3 different recordings just to have ease of access. All right, when you're ready, we'll get to our final example. All right, so let's get to example 4 here. And this is very similar to example 2 from our part 2 of this lecture. Now, if you want, go back and review that first. It's virtually identical. The only thing that changes is it's a different type of function. Example 2 was a simple cubic function. Here we have a combination of x's, powers, and exponential functions, e to the x. That's the only difference here. So if needed, go back through your notes, look at the work for example 2 to guide you through answering this one, example 4. We'll check in several minutes. All right, so let's go through part A. Now, again, earlier we mentioned if you aren't sure what to do, most questions at this phase in a Calculus 1 course deal with first calculating a derivative. So if you're not sure what to do, first calculate a derivative. All right, so all the work is up on the screen here just to, again, keep this lecture short and to the point in terms of length for the recorded lecture. You have the benefit of being able to pause and rewind if needed. So for g of x equals 2 times e to the x minus 4x plus 1, we can calculate its derivative pretty easily. 2e to the x differentiates to 2e to the x using the constant multiple rule. 2 is a constant, and you're right, the derivative of a constant is 0, but this is a constant multiple. 2 is multiplying e to the x. So we differentiate e to the x, which is itself. The constant multiple 2 stays there. For x, however, the derivative of x from the power rule is 1, so the derivative of 4x is 4. The last term, 1, differentiates to 0. Okay, that is pretty much the calculus for the question. G of x, its derivative, g prime, is then 2e to the x minus 4. And with the equation of the tangent line in the upper right of the bottom portion below the line, we just have to calculate g of 0, that's your y-coordinate, and then g prime of 0, that's your slope. So if we plug 0 into the function g, just recall that e to the 0 is 1. Anything to the 0 power is 1. So we can do this calculation without a calculator. We get g of 0, 2 times e to the 0 plus 1. That's just 3. And similar result for the slope, g prime of 0. We get that g prime of 0 comes out to negative 2. Okay, that is done. We just plug in our y-coordinate, 3, and then our slope, negative 2. that slope we calculated from a derivative, I find a lot of students, because we made the connection earlier with tangent lines, first answered with the limit definition of the derivative. Notice we no longer have to rely on calculating a derivative using the limit definition, which was when we first encountered the tangent line problem. So from here on, never use the limit definition of the derivative for any calculations unless you're asked explicitly in a question to use the limit definition. So we apply our differentiation rules to find g prime here of x. Okay, so just plug all this in and we get this equation for the tangent line in simplified form, y minus 3 equals negative 2x. You can add 3 and express it in y equals mx plus b form, slope-intercept form, rather easily. All right, either form is fine. You don't have to solve your equations for the tangent lines for y. Okay, so really here, the calculus occurred in calculating the derivative g prime of x. Currently, it's not too bad, since we only currently have access to very simple differentiation rules. That all changes once we get access to the product and quotient rules, which is the next lecture. So right now, this is the calm before the storm. All right, when you're ready, we'll take a look at part B, which also relies on having the derivative g prime of x that we found here. All right, let's go through the last part. All right, and the only new part here is we get a different type of equation. So we still take as our starting place having the derivative. Still the same, g prime of x is still 2e to the x minus 4. But now, to find where the tangent line is horizontal, recall from example 2, we saw the connection. A horizontal tangent line implies we're looking for where the derivative equals 0. Make sure you see that connection. Slope of a tangent line comes from the derivative. The slope of a horizontal line is 0. So we combine those two ideas to get this simple concept, solving for what values of x make the derivative equal to 0. Now, the calculation of the derivative here isn't difficult. It's not the calculus. So we get a simple looking equation. I find a lot of students in my calculus courses get hung up here because their kind of ideas from pre-calculus could be a little lacking. So here, I don't want to say we have an algebra problem, but hopefully a familiar pre-calculus problem. Here, we're just left with an exponential equation. Now, let me get you to the point where most students get stuck. You can isolate and solve for the exponential function, add 4, and then divide by 2. So let me pause here and see just how well those ideas come back. So see if you can complete solving it from here. That'll give you a good gauge of how well you understand algebra and pre-calculus. We'll check in a few seconds. Pause if needed. All right, are you ready? Here, the stumbling block is not algebra, but kind of pre-calculus ideas. Now, we've got it to the point where we've isolated the exponential function. We have e to the x by itself. And we are going to try to cancel that. We always cancel a function. We undo a function by using its inverse. Now, to get technical with terms from your pre-calculus course, what is the inverse of an exponential function? A logarithm. And here, since we're using exponentials base e, we use logarithms base e, which is what's called a natural logarithm, written notationally as ln for the natural log. Okay, so from here, we can cancel the exponential function by taking the natural log of each side. Just like we would cancel a square root by squaring each side, we cancel the exponential function by taking the natural log of each side. The reason we do that are those cancellation properties in red. You might have called them the cancellation or inverse function properties for exponential functions and logarithms. All right, that's what I find most students either forget or they never learned it as thoroughly as they should have, but it's the key here. We take the natural log of each side because natural log of e to the x cancels out to x. So we here have solved for x, we got x by itself, and we find that our x coordinate, where the tangent line is horizontal, occurs at x coordinate natural log of 2. Now we should, since the question asks to find the point on the graph, we should find the y coordinate, but it doesn't work out to be anything nice since we kind of have some natural log values in there. You can get an approximate decimal value, but the exact value isn't important or pretty here. So for my course, that's as far as I would find it's okay for a student to take it. Getting to here that at the point with x coordinate equal to natural log of 2, the derivative equals 0, which means the tangent line is horizontal. All right, and this concludes our third part of this lecture. This was the third recorded part 3, and this completes part 4 of the lecture content, derivative of exponential functions. Make sure you go back to part 1 to review the 4 parts: derivatives of constants, derivatives of powers, derivatives of polynomials, and finally now, derivatives of exponential functions. We took our time with this lecture since it's kind of a transition going from kind of the before to now having access to differentiation rules. So the big rules to take away from this lecture: the derivative of a constant is 0, the power rule, and then the derivative of the exponential function. E to the x is itself e to the x. We'll be applying those examples and functions and derivative rules again within the next lecture when we get to the product and quotient rules.